This is the third problem. You're getting the knack of it. And let's write this down. So reset. By the way, I'm not defining x to be a variable because in Sage it's automatically a variable. So I'm just going to say f of x. What's f of x? It's x cubed. He uses rather straightforward problems, by the way, but it's surprising Newton's method is quite good at even more complicated expressions. Not always, by the way. Sometimes it goes wacky. So let's say plus 18. And what's nice about the key, whoops, I made a mistake. I just noticed that. I'm going to go back over it. I'm going to put an equal sign there. Sorry about that. All right. So I'm going to do df. We've done that before. What's df? It's I'm defining another function. It's, I'm going to say it's a derivative of f of x with respect to x. And then I'm going to define another function called Newton's method. And Newton's method is x minus f of x divided by df of x. All right, and I'm going to hit return. And like before, I know there's a graph over there, but I'm going to plot f of x, and who knows what's going to happen. Let's see what happens. And I'm seeing a picture over here. And by the way, this is why sometimes people looking at Sage are curious about why I'm not seeing the same picture over here. And I gotta change the viewing window. So let me close these out. And it's another onus on me to do that. And I'm going to say x min is equal to, I'm going to say minus 3. And the x max I'm going to say is 5. Let's hope I didn't make any mistakes. But the nice thing about Sage, if I make a mistake, it's going to tell me I made a mistake. So I got a better graph now. And someone's going to say, well, I like the graph that on the paper better. It doesn't matter. I can certainly approximate the root now. All right. Now I'm looking at it, and I'm going to say the only root to this over here, it looks about minus 2.2 to me. So I'm going to make my first guess. Whoops, I'm sorry about that. I'm going to make my first guess to be equal to minus 2.2. All right. And now what I want to do is I want to get another guess, and I want to get another guess would be x1, and I use Newton's method to do that. And it's going to be assigned a Newton's method at x0 or x0, and I want to display x1 and see what happens. Okay, I get that number. So it's not really minus 2.2. It's saying its root's really close to minus 2.17. But again, within nearest tenth, it's very close. All right, I want to do another guess, x2, and we're going to do this until no change has occurred. And that's going to be x1, and we want to display x2 now. And let's see what we got over there. There's a slight change, by the way. Right, I want to keep going. I'm going to do x3 now. And what's that equal to? Newton's method evaluated at x2. And I want to display x3. And let's see if there's been a change. There's certainly been a change. Let's go to x4. And that's going to be Newton's method evaluated at x3. And I want to display x4 now. And again, I'm looking to see if there's a change in the number. Now, looking at it, there's no change in the number. So this is the my machine's current level of precision. Oh, let me go back to Sage. Sorry about that. So what I want to do is I want to scroll through the notes. And certainly, I took the same initial guess. No surprise there, by the way. And then these numbers here are matching up beautifully. And pay attention to that. Again, I want to also point out in the notes, I also use Wells's version, and they're the numbers for Wells's version as well. Do they converge to the same approximate root? Yes, they do. Thank you.